Okay, so today, you guys, you had some assignments last week, and I know there were quite a few problems on those, but it's one of those skills that just needs some review and some practice. Factoring is one of the most important things we do. We do a ton of it in my AP Calculus class, so it's not something that ever goes away. We just, that's one of, and why do we factor so much? Well, we factor so much for various reasons, but essentially they all boil down to a similar concept, and that is that it helps us to solve equations or find zeros of equations. Okay, for now, we're just going to think about that as solving equations, though, and later on we'll also realize why that's just another fancy way of saying find the zeros or the roots of an equation. Okay, so when we want to solve by factoring, there's really just three parts to this. First one is we put the equation in standard form, which really just means, let me go in here and I'm just going to add another little piece to the notes. That really just means that we are setting the equation equal to 0. I'll do it like that maybe, okay? And so that's first step, put the equation in standard form. In other words, we're moving all the terms to one side, so we set it equal to 0. Then we're going to factor it using all the skills you've been practicing since last time we met, and then apply the zero product property. Okay, so let's look at some examples, and we'll go through these steps for a few examples, and I'm going to make this, I want to hit a couple different kinds of examples that I've chosen for reasons you'll see, but then I want to give you some time to work on this stuff too. Okay. All right, so solve the equation by factoring. So talk me through this, and in chat, you guys can maybe just contribute in chat here, so I don't have to, it might go a little quicker if we do it that way today. So what can I do? How do I factor this? What do I do?
You could factor out a 4x.
Okay, good. I could factor out a greatest common factor. Remember, that's always my goal, is I'm trying to factor out a GCF if I can, and I can. Right, I can factor out a 4x, which is my GCF, and what's left behind if I do that? If I undistribute a 4x, what do we have? 4x times what is 4x squared?
X plus 3.
There you go, good. And then 4x times what is 12x? 3. Okay, good. So it was already in standard form, so there was step 1. We got it factored, there is step 2. And now we apply that zero product property, right? Remember that warm-up I had you do last time where I had you do some bizarre combination of multiplying a whole bunch of stuff in your head, and then when I told you to multiply by 0, everybody had the answer, right, immediately. Because as soon as you multiply by 0, something by 0, you know you're getting 0 for a result, and that's the concept at the core of the zero product property. If I can factor an expression and it's in standard form, so it's equal to 0, well, the only way that this product of factors can equal 0 is when the factors I'm multiplying by 0. So the only way that could happen is either if 4x equals 0 or x plus 3 equals 0. And what makes that happen? 4x is equal to 0 when x equals 0. X plus 3 equals 0 when x equals negative 3. So those are my two solutions. Okay? Now, I'll make one other point here, and there's sort of a fork in the road on this one. So the other way you could do this, and it's a very minor difference. We cannot divide both sides of an equation by a variable, right? When it's in standard form like this, agreed? Because I'm going to lose a solution if I do that. If I divide both sides by 4x, I just get x plus 3 equals 0, and I only get one of my two solutions. But I can always divide both sides of an equation by a constant. So one thing I could do here is I could divide both sides of this equation by 4 and get x squared plus 3x equals 0. And now if I factor out an x, I just get x times x plus 3 equals 0. And this gives me my same solutions, doesn't it? I get the solutions. When I set this equal to 0 and apply the zero product property, well, the factor x equals 0 when x equals 0. and the factor x plus 3 equals 0 when x equals negative 3. So do you divide both sides by 4, or do you just factor out a 4x? Doesn't matter. Whatever you prefer. Either one is fine. Okay? All right, so moving on here. How about this one? How do I solve this one? By factoring. What am I going to do here?
I can't remember what you would call it, but they're all squares.
Okay, good. Yeah, so this is the difference of squares pattern, isn't it? Right, the pattern we want to use here is the pattern a squared minus b squared equals what? What does that factor into?
A minus B times A plus B.
There you go. A plus b times a minus. Doesn't matter which order you write them in. Makes no difference. The product of a plus b and a minus b, right? So then our goal here is, can we write this as something squared minus something squared, a difference of squares? Well, we can. What do we square to get 25x squared? Good, the quantity 5x, and then 36 is just 6 squared, right? And so this fits our pattern. A is 5x in this case. B is 6, so 5x plus 6 times 5x minus 6. And that whole thing is equal to 0, right? We've got it equal to 0. So now we just apply the zero product property. And what are my solutions going to be? What's the 0 of that factor? If I set it equal to 0 and solve, what am I going to get? Well, just do the steps in your head. If I've got 5x plus 6 equals 0, what are the two steps to isolate x? If I've got this set equal to 0, do this in your head. What are the steps to get the x by itself?
You'd subtract 6 and then divide it by 5, so it'd be negative 6/5.
There you go. Good. I'm going to subtract 6 to the other side, and then I'm going to divide that by 5 and get negative 6/5, right? Or, same thing over here. This time I'm going to add 6 to the other side and divide by 5. So we can just do that stuff in our head, right? Okay, we good with that? Okay. All right, so moving on. What about something like that? What should I probably do there? It's in standard form. It said equal to 0, but could I write it in a better standard form? Yeah, let's clear the fractions, right? If I multiply both sides here by 6, if I distribute a 6 through the whole thing, well, the 6 is going to cancel, right? So I'm going to get a z squared, 6 times negative 5z over 2. Well, look what's going to happen there. The 6 over the 2 is going to reduce to a 3, which I multiply by the top, right? And I get a minus 15z minus 6 times 36 is 216. So there's maybe a better equation, right? Okay, what did we just do there? We did something in math that is really a great trick that we do all the time. We traded our original equation the original equation for a different equation with the same solutions. Okay, We do that all the time. There's an easier one to solve. So how do we solve that one? It's in standard form. How do I factor it? And by the way, before we go any further with this technique we call solving by factoring, later on down the line when we're solving a bigger variety of quadratic equations, is solving by factoring always going to work? It's not, is it? Because not always are we going to be able to factor quadratic trinomials, right? It's not always going to work that way. Sometimes we're going to get trinomials that don't factor, that still give us solutions. And so what we're moving towards at the end of this unit, we're going to become much more strategic about this. This is just our first line of defense, our first strategy, because it's the easiest, right? When we face quadratic equations, after we put them in standard form, eventually we want to solve these things strategically, so we're going to always solve them the easiest way possible. That is a trend that continues right on up through calculus. And really, a large portion of what I teach in AP Calculus is not how to solve calculus problems, but how to solve them most easily, right? That's always our goal in math, is to be efficient. And so this is the easiest way to do it. If we can solve by factoring, we will. But if we can't, then we move on to another technique that might be a little more time consuming, okay? Well, this is one where A is equal to 1. And so if this factors, what has to be true? What has to be true of my magic numbers? M and N have to do two things. They have to multiply to what? What do they have to multiply to?
Don't they have to multiply to A times C?
Right, which in this case is just negative 216. Everybody agree? Okay. So they have to multiply to negative 216 and then have to add to what?
Negative 15.
Negative 15. So let's play the sign game, first of all. What can you tell me about the signs of M and N if they multiply to a negative?
One's positive, one's negative.
Okay, one's positive, one's negative. Which one is negative? Or sorry, which one is bigger? Gave it away. The positive or the negative?
The negative one's bigger.
How much bigger?
15.
15. There you go, right? So we got two ways we could do this. If I'm trying to find M and N, I could either find all the factors of negative 216 that add to negative 15, which is fine, or I could just find a positive and a negative number that add to negative 15 and multiply to negative 216. Now, I want to do both of these just this one time, just to make my point. Okay, so one way we could do this is we could say factors of negative 216. We could find all factors. Okay, so we know that the negative is bigger, right? So we'll just make our choices here. So we could do something like, I could do negative 216 times 1, but that product is way too big, right? Or when I add those up, I get negative 215, which is way too big. They have to add to negative 15. So I could go down the list. I could do negative 108 times 2, but obviously that's still way too big. Go down the list further. Does 3 go into that? It does, right? So I could do negative 72 times 3. Still, those add to way too big a negative number. But I want you to notice a trend here. If the numbers are really disparate, if they're very far apart, one is big and one is small, the sum is always going to be big. As the numbers get closer together, then what happens? Well, the sum gets smaller and smaller, right? So we know in this list that we can cheat a little bit here, right? We know that we need to skip down a little bit. These numbers are way too far apart. So let's go down and see if we can pick some numbers that are a little bit closer together that multiply to negative 216. Like what about 6 and what? 6 and 16? So if I did negative 16 and positive 6, well, that's not right, is it? That's 6 and what? 6 goes into that 36, right? 36 and 6. Yeah, there we go. That still is adding up to negative 30. So they even need to get closer than that, right? So what else could I do? I go down even further. Let's see. What about like 12? 12 goes into 21 once with 9 left over. And let's see. Does 12 go into that evenly? It should, right? Yeah, it should. 12 should go in 18 times. Is that right? Yeah. So negative 18 and positive 12. Well, now those add to something too small. So we know it's in between here somewhere. Can anybody come up with an answer? It's almost easier in this case. And there's a lot of technique in math. I want you just to really think about this for a second. It's almost easier to work with the ends, isn't it? Because we're dividing smaller numbers into 216. So what's another number between 8 and 12 that works? 8 doesn't work, does it? 10 doesn't work. What's one that does work?
Is it negative or 9?
Okay. So what about 9? Yeah. 9 goes into negative 21. Let's see, 2 times, right? With 3 left over. So 24. There you go. Negative 24 and 9. And what do you know? That adds up to negative 15. So that's our winner. Okay. Now compare that to why did I go through all this stuff? Because there's going to be a point to this. So now what if we did this the other way? What if we instead of trying to find factors of negative 216, which is kind of hard to do, if I've got a big number like this, finding the factors of that is a little bit tough, right? We could make a factor tree also, which might simplify things a little bit, right? But in this situation where I'm trying to find factors of a negative number that add to some positive or negative, where I know that in this case, the two numbers, the negative one is exactly 15 bigger, I would claim that in this situation, when they're multiplying to a negative like this, it's easier instead to make a list of numbers that add to negative 15 and figure out which one has the right product, right? They have to multiply to negative 216. So let's make a different list here of M and N. Oh my gosh, this darn pen. And this time we're doing what's M plus N for our other, we got, M times N, sorry. Okay, numbers that add to negative 15. Well, obviously the easiest one to pick would be like negative 15 and 0. That's no good. What about negative 16 and 1? Well, those multiply to something way too small. So these numbers need to be quite a bit bigger, right? So we could do let's skip down the list a little bit. If we did like negative 22 and positive 7, we're still too small, aren't we? That's too small. So we got to go down a little further. Well, we could, it's quite a bit too small, right? It's only 154, negative 154 instead of negative 216. So our next logical step might be to just pick negative 24 and 9. And what do you know? Then we get it. That's negative 216. So I would argue that you get your winner a little bit easier that way, right? Does that make sense what I'm saying? It's not like that's critical that all makes complete sense, but all this stuff makes it a little bit more strategic, right? You're able to find those numbers a little bit more easily. And remember, the whole point of solving by factoring is it's got to be easy or it's not worth doing. We'll move on to another technique anyway, right? And so the way to make this easiest is really to, in some cases, to go with the orange strategy instead of the green strategy. Okay, now that we've got this thing factored, though, it's a piece of cake, right? Now we know this factors into z minus 24 times z plus 9. Now the answer is easy. What are my solutions? Either z equals what?
24.
24, or z equals
-9.
-9. There you go, right? Okay. Now, a real common mistake that people make when they're solving by factoring is they quit too early. They figure out what the magic numbers are, and then they write down their solution is z equals -24 or z equals 9. But remember, the magic numbers are not the solutions. Those are just the numbers that we get when we factor, right? We've still got to do that one additional step of applying the zero product property, right? So don't fall prey to that really common mistake. Okay, real quick, I want to get through these. What about this one? What have I got to do here? First step.
You got to get the equation equals 0, so you're going to have to remove the 65x.
Okay, I could either move the 65. I got two options here, don't I? I could either subtract the 60. Say it again.
Or you could go the other way, so then you'd have a positive 8x squared if you want.
There you go, right. So if I subtracted 65x from both sides, that's going to give me negative 8x squared minus 65x plus 63 equals 0. And I never really want to have a negative value of a. It always makes it harder, okay? So if I've got a situation like this where I've got a negative value of a and I've got my quadratic equation in standard form, well, we're going to do something similar to what we did up here. We're just going to make an easier equation, right? Last time we distributed a 6 through to clear the fractions. This time we would just distribute through a -1 to turn this into a positive 8x squared plus 65x minus 63. It makes it easier to factor. In fact, it makes all of our different methods we could use to solve quadratic equations easier when you put it in standard form to make a positive, right? And so Andrew was right that probably an easier way to do this would be to skip that whole process and just maybe push everything to the side initially that makes a positive, right? So we'll push everything to the left and get our 8x squared plus 65x minus 63 equals 0. Okay, and now we got to solve this by factoring. In reality, we probably wouldn't do this. In reality, when we get down to the end of the unit, when a is not equal to 1, if we've got big numbers like that, we probably won't bother. We'll probably just use a different technique for solving that equation. But for now, let's go ahead and I'm going to throw a couple at you in this assignment where you got to solve by factoring. So this is one where a is equal to not equal to 1. Unfortunately, I can't factor out a GCF here to make this easier, can I? There is no number that divides into 8, 65, and 63 other than 1. So I'm stuck with a harder factoring problem where a is not equal to 1. We got to find magic numbers. Okay, so we know that m and n have to multiply a times c. 8 times 63 is what? Negative 264. Oh, no, it's not. It's negative, what am I doing? Negative 504, is that right? Did I do that right? Give me a thumbs up. Is that right? Okay. So A times C is negative 504. B is positive 65. So I'd have to I've got to find magic numbers that multiply to negative 504 and add to 65. right? So we could do, this is one where we know the sign of one is positive and one is negative. In this case, M is the positive. It's the bigger one, right? And they have to, this is negative, and they have to add to 65. So M must be 65 bigger than N. Agreed? Right. So if we were gonna find magic numbers here, it'd be easier just to start with a bunch of numbers that add to 65, right, and see which ones multiply to give us negative 504. Okay, well, what are some numbers that multiply to 65? What if we started with something like, what if we started with positive 68 and negative 3? That's not big enough. That product is too small, isn't it? So we got to make the product bigger. What if we did something like, let's bump this up a little bit. Let's bump this up to negative 5. So that would bump this up to 70. Still too small, right? Negative 5 times 70 is still only negative 350. It needs to be negative 504, so we got to bump it up some more. Let's bump it up to negative 8. Negative 8 and 73. How are we doing with that? That's going to be, what's that? It's going to be a little too big, isn't it? That's going to be 5. That multiplies to negative 574. Is that right? Am I doing my math in my head right here? Or sorry, 584. So it's too big. We got to back off a little bit. Right? We went a little too far with it. It's got to multiply to negative 504. So this is probably going to be our answer. 72 and negative 7. Right? If we multiply those out, sure enough, we get negative 504. So those are our winners, right? 72 and negative 7. Okay? Give me a 1 to 5 on that. Is everybody good with that? Okay? Okay, and once again, we would probably not have used this technique, right? This is probably a little bit of overkill for solving by factoring, but we always want to over practice things. So then we know these are our magic numbers, 72 and negative 7. So remember, we're gonna solve this by grouping. We're gonna split that middle term using our magic numbers. So we're gonna rewrite this whole thing then as 8x squared. Instead of 65x, we're going to break it up into plus 73x minus 8x. I always like to put the negative, if there's a negative and a positive, put the negative first so I can put a plus sign in the middle. So I'm going to make that a minus 8x plus 73x minus 63. Okay. What happened here?
It's supposed to be negative 7 plus.
Oh, yeah, that's supposed to be a negative 7. Right. Yeah, I did the wrong one. No wonder. Yeah. You say, gosh, that's not going to work. But these are my magic numbers right here, aren't they? Come on. There we go. Okay, so yeah, we get a negative 7x plus 72x. And now we can just split this thing in two, right? Our first group, think about how we factored by grouping. We had to factor out the greatest common factor. What's the greatest common factor of 8x squared minus 7x? Just type it in chat. Yeah, it's x. Good, I can factor out an x. So if I factor out an x, my binomial factor that I'm left with, if I divide both those by x, is just 8x minus 7, right? So now I've got plus. What can you tell me here about what do I know for sure about my second group?
It will have the 8x minus 7.
Good. Okay, I know the binomial factors need to be a common factor. So that's going to be an 8x minus 7. And then we just have to ask ourselves, well, what goes here? Okay, what do I factor out to make that happen? Well, I could factor out a 9, right? Everybody see that? And so now I've got common binomial factors that I could factor out of each term. And what's left behind if I do that? Well, I've got an x from the first term plus a 9 from the second term, and we got a factor, didn't we? Okay, so this is equal to, this whole thing factors into, we can go up here now. Let's go up to this one, right? So we got this factored. This factors into 8x minus 7 times x plus 9, and it's all equal to 0. So now we can apply the zero product property and solve for x, and I get 7/8. I'd add 7 and divide by 8 if I set that equal to 0 and solve. Or -9, right? Okay. And then finally, maybe we won't even do this one, but you just tell me what would I do. This looks like a pretty ugly problem. I've got a combination or product of quadratic factors, right? So it's in standard form. And later on, we're going to deal with big, larger polynomial equations that we've got to factor that are even bigger than quadratic. And so this might be a step we'll end up with later in the year. When I get to here, I always have to ask myself, can I go further with this? Can I keep factoring, right? I've got quadratic factors. Maybe those go further. Maybe they do, maybe they don't. Well, let's see. How about this first one? These are both easy ones, easy quadratic trinomials to factor because a is equal to 1, right? So are there magic numbers that multiply to 15 and add to 8? Yeah, right. 3 and 5, right? So I can split this one into x plus 5 times x plus 3. What about this guy? I can split this one up easily too. That's got a 1 in front of the x squared. So either it's going to work or it's not. Either it factors or it doesn't. Are there numbers that multiply to -12 and add to -1? Yeah, -4 and plus 3, right? Okay, and that whole thing is equal to 0. Well, there is one moral to this story. Look, I've got an x plus 3 times an x plus 3, right? So I could rewrite this whole thing if I wanted to make it a little simpler as x plus 5 times x plus 3 squared, right? I've got an x plus 3 times an x plus 3 times an x minus 4 equals 0. So what are my solutions then? Well, what's going to be the 0 of that factor? -5, right? So either x equals -5 or these gave me the same solution, didn't they? Right? Which I can see here. What's the solution of when is x plus 3 squared equal to 0? When x equals -3. When is x minus 4 equal to 0? When x equals 4. So we get 3 solutions from this. Now, this isn't important to us now, but I'm going to mention it because we'll talk about it later. This guy right here is unique, though, because this factor appeared twice. What does that mean? That means that solution right there has a multiplicity of 2. We don't care about that for now, but later on we will. That's what we call a double solution. Okay, it's only one solution, but in some ways it counts like 2. And we'll talk more about that later. Okay, I got to let you work here. I didn't anticipate this taking so long, but I do want to give you some work time. Okay? Have at it. There's an assignment up. It's just, honestly, it's really just more factoring practice, but it's within the context of solving equations. Okay, have at it. I'm going to stop recording, and I'll just be here if you have questions, but you guys just work away.